So in this video, we are going to look at how to get expressions for the efficiencies of reversible heat engines, reversible refrigerators and heat pumps, and how they are useful in everyday problem solving, because reversible heat engines, reversible heat pumps and refrigerators do not exist in real life. But yet, the expressions for the efficiencies and the COPs of these heat engines and refrigerators are useful to design and to improve the design of everyday engines, refrigerators and heat pumps. So let's start with the reversible heat engine. We already derived the efficiency for that in terms of temperatures, but we'll just do that once again, right? So let's say we have a high temperature reservoir at TH, and it's supplying heat to a reversible heat engine by amount QH. The heat engine does work W and rejects an amount of heat equal to QL to a temperature, to a low temperature reservoir at temperature TL, right? Now we know that eta reversible is equal to 1 minus QL by QH, right? Eta reversible is equal to W divided by QH, and W is QH minus QL. So I'm going to write eta reversible heat engine as 1 minus QL by QH, and this is equal to 1 minus TL by TH, based on the previous two videos where we defined the temperature scale in such a way that QL by QH of a reversible heat engine is TL by TH. Now remember that QL by QH is equal to TL by TH only for a reversible heat engine. It's not true for other types of engines, which means if you've got a real engine, then chances are that QL by QH will never be equal to TL by TH. The reason is that all real engines are not reversible, they're in fact very much irreversible, and so therefore for real everyday engines that we will encounter in our lives, QL by QH will never be equal to TL by TH. But if we have a reversible engine, which is only possible in concept and theory, if we do, then eta reversible will be 1 minus TL by TH, right? So this is for heat engines. Let's do the same for a heat pump, for example. So what does a heat pump do? We have a temperature TH at a reservoir which requires to be supplied with heat, and let's say QH, by doing work W and extracting heat TL, QL from a low temperature reservoir. Now you might ask, we haven't discussed this before, but you might ask, why do we need to do all this? Why can't we just use an electrical resistance heater to supply the heat that is required? And you can do that, and then the entire work will then be converted directly to heat, and that is fine. But then you will lose a lot of useful work, and you don't want to do that. So what this heat pump helps you to do is to reduce the amount of electrical energy or useful work that is required to produce heat, because it takes advantage of the fact that energy has a quality, and there is a higher quality for work and useful work and electricity, and a lower quality for heat. And so therefore, if you can use some higher quality work and the rest lower quality energy to produce heat, then you win, because you don't use all as high quality energy, and therefore you use heat pumps, right? And so the COP, as we defined it previously, of a heat pump is defined as QH divided by W, right? This is the definition. Now for a reversible heat pump, I can define it as QH reversible divided by W reversible, right? Now this can also be written here as QH divided by QH minus QL, right? And therefore I can write this as 1 divided by 1 minus QL by QH, right? And from here I can write this as COP of a reversible heat pump as 1 divided by 1 minus, I know QL by QH for a reversible heat pump is TL by TH. So I can substitute that with TL by TH. Again, I can substitute QL by QH with TL by TH only if my heat pump is reversible, which means I can only do it as a concept, as a theory, right? But why do I do it? Why do I have to write this reversible efficiency as 1 minus TL by TH when I know that I can never achieve this efficiency in real life? Why do I write COP of a reversible heat pump as 1 minus TL by TH when I know that I will never be able to achieve that for a real heat pump operating between these two temperatures? The reason we do this is because we want to compare a real heat pump or a real engine with that of a Carnot heat pump or a Carnot engine, or basically a reversible heat pump or a reversible engine operating between the same two temperatures. So let's say I have a heat pump and it gives me some COP. I can compare that COP with this value here, and I know that it will always be less than this value, but I can compare how close it is to this value, right? So let's say, arbitrarily speaking, I have COP reversible heat pump, let's say is 4. My COP of my real heat pump is, let's say, 3.5. Then I know that I'm close to the reversible heat pump COP, but there is room to improve, which means there is a possibility to improve this heat pump further, but usually that comes at a cost. Usually that comes at a cost of materials, cost of volume or space or weight, or cost, basically, right? So sometimes I might choose to try to further improve this, or I might just live with that. So that's a choice that I can make later, but I can make that choice only if I know how I stand with respect to this value here, right? And so that's why we take up reversible heat pumps, reversible engines, not because we can achieve them in real life, but because they serve as models for real engines and real heat pumps and real refrigerators, and we can see how close we want to get up to the maximum possible efficiency or the maximum possible COP. So similarly, we can also do this exercise for a refrigerator, and as we discussed earlier, refrigerators take heat from a low temperature reservoir. Basically their job is not very different from a heat pump, except that for a heat pump the focus is the delivery of heat to the high temperature reservoir, whereas for a refrigerator the focus is the removal of heat from a low temperature reservoir, both for refrigerators as well as air conditioners. So when I say refrigerator, it also accounts for what we do with air conditioners in general. So I have a refrigerator, a reversible refrigerator, removes heat QL from a low temperature source, pumps heat QH to a high temperature source, and in the process it needs us to do a work W, and we have previously defined COP of a refrigerator as QL divided by W, right? The difference here being this is QL by W and here QH by W. So this is the definition. This is always valid, right? So this is whether or not we have a reversible refrigerator or an irreversible or a real refrigerator, this definition always stands, okay? What we are trying to do now is to derive an expression in terms of temperatures for a reversible refrigerator, right? Which is obviously not applicable to a real refrigerator. I am trying to repeat this again and again because this is a very common error or a mistake that students make, in that they believe that the COP of a refrigerator is what we are going to derive now. It is not. What we are going to derive is the maximum value the COP of a refrigerator can have operating between the same two temperatures, right? So this is equal to QL divided by QH minus QL, and I can always divide this by QL and write 1 by QH by QL minus 1, and so this is so if I have a reversible refrigerator, then I can write this as 1 by TH by TL minus 1. Remember again, that this is only for a reversible refrigerator that I can write QH by QL as TH by TL. If I don't have a reversible refrigerator, I should stop here. So that's how the expressions for the efficiencies of a reversible heat engine and a reversible heat pump or a refrigerator can be derived based on the fact that we have defined our temperature scale in a very convenient manner, and that came from the second law of thermodynamics.